Okay. Lab is the oxidation of the diol. That is a report. Okay. Not the worksheet, but a report for that. Okay. Do when you come to lab next week. Next week, though, in lab, instead of doing a lab next week, I want to have a review session, and we will talk about the 8-week lab. Mainly talk about the 8-week lab next week. So, no lab next week, so there's no pre-lab to prepare for next week. Okay. Let's move ahead. Any questions about NMR before we get started? Everybody good with NMR? Questions about NMR? Yes?
On carbon NMR, whenever you have the same with no H's and a broken aromatic ring, are you able to determine like if one's being pulled by nitrogen or one's being pulled by oxygen, like which one would be further down the line?
I can't quite hear you. Tell me again.
Like on carbon NMR, if both of them in the aromatic ring.
Anybody here?
On carbon NMR, when both of them is in an aromatic ring, if neither one of them have like a hydrogen attached to it, if one's being pulled by like a nitrogen.
That's what I understand it. Neither has a hydrogen attached to it.
Like because they're attached to other things, like a double bond and then another carbon, and then like a nitrogen, and then one's attached to an oxygen. Are you able to tell which one is pulled more and will be further down?
I'd have to see an exact example of what you're talking about, because I just can't follow you. You said because they're not attached to hydrogen. I'm trying to figure out what the relevancy of that is.
So like with this carbon, like which carbon is being pulled more? Is one attached to nitrogen and that one attached to oxygen?
That can be difficult to tell in an aromatic ring. But why do you need to be able to tell them? I'd like to see what the exact issue is, because I got to determine the relevancy of your question, how important it is, where you're coming from, and so if I see an exact example that you're working, I can say it might not be that important.
It was on the post slide.
Oh, for our last one?
It was for assigning peaks for the carbon NMR. And you
In what?
The post
for
slide.
the worksheet that we had to do for last week's lab that was due to.
With the diol lab?
Yeah.
No, not for the
Not
dial.
that.
It was the synthesis.
And the seed in front of the seed.
Can you show me that?
I turned it in yesterday.
Oh.
I have mine.
Well, if you've already turned it in, let's just wait till we get it back. I would maybe ask before you turn it in. Okay. I would suggest you ask before you turn it in. At this point, let's just wait till you get it back. Okay, oxidation of alcohols handout. Oxidation of alkenes. We've already covered oxidation of alcohols. Alkenes can be oxidized. There's 3 reactions here. I'm actually only going to cover one of them, the ozonolysis reaction. The first reaction is, we can illustrate an alkene. The alkene can be oxidized. The 2 carbons of the alkene can be oxidized. One of the big 3 will do this. KMNO4 with an alkene will convert the alkene to a cis diol. And so each carbon now is oxidized. How do you determine if a carbon is oxidized? 2 main ways in organic chemistry. Gain or loss of hydrogens. Okay. This is not gained or lost any hydrogens. Each carbon has one H, each carbon now has one H. So what's another way to judge redox? Bonds to a more electronegative atom. How many bonds to a more electronegative atom does this carbon have? 0. How many bonds to a more electronegative atom does this carbon have? 1. Now some people will say bonds to oxygen. That's an oxidation. Makes sense, right? Bonds to oxygen. But more broadly, it is bonds to a more electronegative atom. Because that will help you be smarter. We may not have mentioned that before when we talked about alcohol oxidation. Primary alcohol oxidized to the aldehyde. How many bonds to a more electronegative atom for this carbon? 1. How many bonds to a more electronegative atom now? 2. Double bond to oxygen. Do you see? So if we look at it that way, that's an oxidation. You can also look at it in terms of losing H's, because the carbon is also lost an H. So you can see it both ways. So, you can do this reaction. Okay, you can look at the mechanism. It involves a manganate ester. Very similar. If you start with the alkene, attack the oxygen, these electrons move here. These electrons will move here. It's all concerted. Stereospecific addition. The manganese ester is not stable. With water, it'll get cleaved. And those two will become H's, and that's how we get this. And it's a cis because it's a stereospecific addition. The manganese is on one side of the pi face.
Does it take 2 water atoms? Like 1 H from each one, or both H's from 1 water atom?
You mean here?
Yes.
It's probably multiple waters. But don't really worry about the mechanism there. Okay, so this is an oxidation. This can be done. Another reaction that is in this handout is another way to do it is with osmium tetroxide. With osmium, you have to have a second step. It's very similar. If this was manganese, we have the similar structure as shown, except one of the oxygens would be minus. Because manganese can't have as many bonds, I reckon. You have to look at the structure. But with osmium, the whole thing is neutral. That's a neutral molecule. Very similar to the manganese mechanism. We get the osmate ester, but it is actually stable. And for it to break down, you have to add another reagent. You can either add peroxide, hydrogen peroxide, that's an oxidant. This is actually a reducing agent. 2 different mechanisms, but either one of these will cleave that to the diol. You get the same product as with KMNO4 on the previous page. The difference is, with KMNO4, the yields can be low sometimes. Osmium, you get higher yields of the cis diol. Problem is, osmium is quite toxic. So do you want good yield and safe, or, bad yield but safe, or great yield but toxic? What's your preference? Well, it can depend. Osmium tetroxide is sometimes been listed as a war crime agent, I think, used in some nefarious purposes because it has quite high toxicity. So you've got to be careful with osmium tetroxide. It's actually, I think, volatile. If you're weighing it out or something, you can inhale it. I think. I've never used it. Okay, but on paper it looks nice, right? Nice and friendly? Okay. Why would you want to make diols? Here's a diol. Okay. called a 1,2. What's the term we use when things are next door to each other? In organic 1, we made, if you take an alkene, you're reacting with bromine, you get the bromine's adjacent carbons, transition. Bisphenol, yes. The 1,2 bisphenoldiol. Guaifenesin is a decongestant, very common. Guaifenesin can be made by what? How could you make it? Please tell me if you can see this, because these other markers, for some reason, aren't erasing anymore. Up there? Osmium tetroxide followed by, let's call it a magic step. Leave the osmate ester. Give the diol out here. There's no stereochemistry, there's no relative stereochemistry, so we don't need to show the cis there. Yeah? That can come from that alkene, that's what we're doing. How would you make that? That is, back this up to what? What bond could you make there? Let's focus in on up here. They're both two different ethers. Let's focus in on this ether. How would you make that ether?
So if you had like bromine or something and then
Can you show a synthesis of that ether? Focusing on the top ether.
if that was an alcohol at the top and then you had like sodium and then you had your alkene. No.
Anybody got something? I would back this up to this phenol. And coming this way, I would react it with what first?
Can you use sodium metal?
Not an acid.
Sodium metal.
Sodium metal. Anybody else? Sodium metal would theoretically work, but with phenols we don't need to use sodium metal, only with alcohols. Phenols are more acidic,
That's right.
and thus we can use sodium hydroxide or sodium carbonate, like that. Using sodium would be like killing a mosquito with a bazooka. It's just not needed. Okay? So instead of sodium metal, let's use something much more common and a little bit safer, sodium hydroxide. Okay? That'll make this the anion. Good nucleophile, then what? Cl there. I use Cl because that's more common. That's called, what do you call a alkene with this carbon? What's this carbon called? The what carbon? Carbon next to an alkene? Allylic. What's carbon next to a benzene? Benzylic. Okay. This is called allyl chloride. Allyl chloride is quite common, much more common than allyl bromide or iodide. Because chlorine is not the best leaving group, why is this more reactive with the double bond there? If the double bond was not there, this would be less reactive. Why is that more reactive for SN2? We covered it in organic 1.
Because it's stabilizing.
Jamari?
Some stabilization from the alkene,
Well, stabilization of what?
the carbon cation.
No, we're doing SN2. There's no carbocation here. That's a primary carbon, although you do have resonance. No, this SN2.
Is it during the transition phase that it becomes more stable because
Yes,
of that?
during the transition state, we look at that overlap of the, it takes on like a p orbital in the transition state. If there's a p orbital next door, we'll stabilize the transition state here. We talked about that in organic 1. Yes. And so since you have this stabilization of the transition state, this sort of enhanced reactivity, chlorine is a superfine leaving group. Okay. So that's why allyl chloride is very common and quite toxic. I mean, even though it's Cl. Where if you just had, well, three carbons, this is not as toxic because it's not, the transition state is not activated, right? This is actually used for some dermatological procedures. It's a gas and it will numb the tissue. Okay, you would never use that in okay, toxic. All right, we explained why in organic 1, right? Everybody's seen the SN2 transition state. The sodium hydroxide makes the anion, and then the anion comes in here to do SN2, and we make this bond here. Yeah. Okay, I show you that to practice some synthesis, talk about that. But this is called, this molecule is called guaiacol. Guaiacol, and that maybe is where the term guaifenesin came from. Because it's made from guaiacol. Where did the term guaiacol come from? I don't know. That's phenol. You put a methoxy next door, which we'll learn is the orthoposition. That's called guaiacol. I don't know. Maybe it was discovered in Guatemala. I have no idea. Okay. Could you do this down here? Could you show the product of that and a Fischer projection and tell me if the product is erythro or threto? What?
What do those terms mean?
You haven't seen erythro and threto? Okay, what does erythro mean?
Same side.
Same side when?
And
the Fischer projection, yes. If the erythro on the same side in the Fischer projection is called erythro. If they're on opposite sides in the Fischer projection, it is called threto. You've done Fischer projections? Okay, well then just do a Fischer projection and then look at the two OH groups. We're making a diol, right? If they're on the same side, it's called erythro. If they're on the opposite side, it's called threto. That comes from the 4-carbon sugars. Carbon, erythros and threos, sugars. Yes, it would have to be 4-carbon type. So I covered those, I introduced those terminology in my organic 1. Because now you can tell me which Fischer projection you got. Instead of saying this one, or instead of saying, hey, I got the one with the 2 H's on the same side, you could just say, hey, I got erythro. Anybody got it? Importantly, what type of an addition is this of the 2 OH groups?
It's a syn addition, isn't it?
Syn addition? Cis addition? Yes. Mm-hmm.
So don't they have to be erythro?
No, it depends on how you draw your Fischer projection. Okay, remember how we did these in organic 1? I recommended, what did we do for this guy? It's a stereogenic alkene. By the way, is that E or Z? Is this alkene E or Z? Z is the same side. Yeah? Yes, it's Z. Okay, stereogenic. And most often when you have stereogenic alkenes, you have to really look at the product. Okay, that's an indicator. You got to really look at the product. What did I do? What did I recommend about these to start with? I recommended that you turn them, right? And put the groups forward or back. Yeah? I remember this? Yeah? Yeah? Everybody with me? We certainly did that in organic 1. Did you guys do something like this to begin with? Did you draw products in Fischer projections? Okay. I would turn it like this. Now what do we know about the reaction? What does this reaction do? Osmium followed by magic step produces what? Cis-diol. We can get rid of that. And put one OH here. What did I say about new things? We're going to put the new things in the plane. So I'm going to put the OH straight up. Other OH here, is it up or down? Up. Cis-diol. Up. Now that bond's a little ugly. It looks like it's not even connected here. I could use my pencil and sort of redraw it. Yeah? There's your product. Plus what? Yes, an enantiomer, right? A molecule is chiral. Everybody see it's chiral? Did a little review here. Final exam is comprehensive. Do I agree it's chiral? Okay, now draw that in the Fischer projection. And there'll be one question we'll have to ask as we do this, because it seems a little bit unclear. So that is, you may want to ask for clarification on some point. Exactly, there you go. What do we put at top and bottom? Sometimes in my, I gave you, put this at top and bottom. Okay, doesn't say anything about it. Typically we put alkyl groups at top and bottom and other things on the side. So a phenyl is not considered an alkyl group. I would put the two methyls, since they're both the same, I would put methyls at top and bottom. And certainly the OH groups on the side. And if you remember, a lot of times we did a Fischer, we drew it as is, and then we rotated afterwards. Anybody got the Fischer? And if so, is it erythro or 3O? 3O? Is it 3O? So what she's saying is the OH groups are on opposite sides of your Fischer. That's what you're telling me. That's what, okay. Instead of having to say all that, you just said 3O. I don't know what you mean. Okay. 3O? Okay, I'll do Fischer projection. Remember this? Do we want the ground over here or over here? They're both methyls. Methyl can be up or down. I'll say over here. Okay? If I'm over here, if you're on the ground and I'm looking this way, OH going away. With OH going away, what side's the phenyl on?
The left.
The left. Yes. With OH going away, the phenyl is on the left. What's on the right on this carbon? Yes, methyl. I'll do that as ME. Okay, that's the ME. We can put an ME there on the end if we want. Two methyl groups. Because if the OH is going away, the methyl's coming towards you, correct? If OH is going away, the methyl's on the right. This is how I've always done it. We did it in organic 1, yeah? Okay. Now, feet on the ground. Ground is there. I never want to turn around and put my feet in the air. Keep my feet on the ground. But just kind of move down here. With this OH going away, what side is the methyl on? Left. It's going back. Yeah. With this OH away, the methyl that's on this carbon is on the left. What's on the right? Undrawn hydrogen. There it is in the Fischer. But as we said, and as we asked, and as we clarified, let's put the methyls at top and bottom. If we can rotate this to the top and that to the bottom, and this rotates to give methyl at the top, the phenyl moves here, the OH is here, methyl at the bottom, OH is here, H is here. There it is. Guess what? Plus what? Yes, the enantiomer would be the enantiomer. If we did it, we would get the mirror image over there. Because there's no plane of symmetry, right? That's no plane of symmetry. Methyl mirroring methyl, but OH is not mirroring OH. And you'd have to have a phenyl down here to mirror. Okay? There's no plane of symmetry. There's your product, the high priority groups. In the Fischer on opposite sides, this is 3O. And the enantiomer would be what? The enantiomer is also 3O. Right? Yes. Mirror image, you can draw the mirror image, it would also be 3O. Yes. Mirror image of 3O is 3O. Just like the mirror image of cis is what? Yes. Mirror image of cis is not trans. Question.
Hey, real quick, can you remind me what meso means? Meso?
Meso is an achiral compound, but it has chiral carbons. Because it has a plane of symmetry. Okay, how we do, guys? Particularly those that did not have me for organic 1. Did you guys do things like this in organic 1? Drew Fischer projections? Yeah? So everything was good? Just that you understand how what that's called 3O? Those are the high priority groups on opposite sides. How do you remember erythro and 3O? 3O starts with a T. And if you draw a capital T, you have a vertical line, but then you have horizontals on opposite sides of the vertical line. Both sides, opposite sides. But if you draw a capital E for erythro, the horizontal lines are all what? They're on the same side. So erythro, the groups are on the same side. 3O, they're on opposite sides. Okay? ET. Don't confuse E and Z, because with E and Z, E means what? E means opposite, and that's because E and O are both vowels. Because Z means what?
It's the same side.
It's the same side. So don't confuse the two E's. With E and Z, E means opposite. But with E and erythro and 3O, E means same side. All right? Don't confuse your two E's. E, okay, you got this? Okay, a little reviewing, yeah, everybody good? Next. I'm going to skip the cleavage of diols. I just mentioned here, diols can be cleaved. This will set us up for moving into ozonolysis. A diol can actually, the carbon-carbon bonds can be cleaved. And each carbon ends up double bonded to oxygen. And periodic acid can do this. I'm not going to include that reaction though. Ultimately, I started out by saying I was going to only do this. We did enough of the bisphenol cis diols, KMNO4 and osmium followed by a magic step. So I am including that. Only thing I'm skipping in this handout is the cleavage of the diol using periodic acid, like the previous page. Let's skip to this though. Ozonolysis. Ozonolysis starts with an alkene, and it ultimately cleaves the two carbons of the alkene, and each of those two carbons becomes a carbonyl. You guys have seen this. I don't cover ozonolysis in Organic 1 because it does, the mechanism doesn't fit in with our typical mechanisms of attacking something and back bonding, not as easily, although it is very similar. But the outcome to me fits in better here because we see carbonyl compounds, which also come from oxidation of alcohols. Okay? So we now have a second way to make aldehydes and ketones. One of them is oxidizing alcohols. The second way we're seeing is cleavage of alkenes. Okay? This can be done. Ozonolysis is one of the top 10 reactions in organic chemistry, probably. And usually they all have a name, like a chemist's name associated with it, like Wittig reaction, Diels-Alder reaction, Grignard reaction, or Grignard reagent. Okay? There'll be others with names, people's names. Now, ozonolysis doesn't have a person's name associated with it, but it's still one of the top 10 reactions in organic chemistry. There's about 20 top 10 reactions in organic chemistry. Okay? We'll see them. Okay. Ozone. We use ozone, that's why it's called ozonolysis. Ozone is O3, followed by a magic step. Here's a Lewis structure for O3, ozone layer. Yeah? Ozone layer, it's a strong absorber of UV, and so it protects us from the UV from the sun. And if we lose the ozone layer, we get more UV exposure. Okay? The good news is the ozone layer is coming back, yeah? It's getting larger now. Ozone is also an oxidant because O3 would like to lose an oxygen and become O2. Okay? Now, Lewis structure here. We can also then draw a resonance structure of this. We can move these pi electrons here, and that would give this structure where we have two charges. That's two charges as well. Which one's a better resonance structure? Actually, this one, because we have more bonds. Also, this oxygen doesn't have an octet. And in Organic 1, we said that's very bad. Okay? It'll come to hunt you down. All right? But, and you can do mechanism with any resonance structure, right? We've said that before? Okay. I could do it here. But let's look at it here. And let's go back. Forget about that. Alkene. Alkenes like to attack carbocations, H pluses, right? Okay. Well, here it attacks oxygen plus. And when it does that, what would form over here? Forget about that. If this moved that way, what would form over here? Carbocation. I'm not showing it. Remember how we often said NAF, not actually formed? When was the carbocation not actually formed? When something back bonded. Well, guess what can back bond here? This other oxygen. So as soon as this moves out, this is coming in. I'm not showing an NAF here. You guys don't know what NAF, how I do that organic 1. Okay? You can watch my videos from organic 1. Okay? They're all labeled. Go to alkene reactions, bromination, or something. Okay? Does everybody agree that this electron movement gives that product over there without those mechanisms there? Yeah? Bond to oxygen, this back bonds, right? Bond to oxygen, how did that bond made? It back bonded. You see the arrows? Okay. Well, alkenes will react with ozone to give this. Now, if you did it here, we could just show this attacking here. When you attack there, move those there, and then move these here. This also gives the end down there, right? You can work with any resonance structure. I just chose to move that first and show a resonance structure, even though it's a pretty poor resonance structure. Okay? This is called a molozonide. Now that's MOL, but what does MAL mean in Spanish? Bad. It's a bad ozonide. Okay? Alright? The bad ozonide will rearrange to a good ozonide. The reason it's bad is all three of these oxygens, oxygen doesn't like to bond together that much. You're not going to see strings of oxygen. And 3 is kind of pushing the limits. Okay? That's why ozone's reactive. You're like, well, why is ozone made? Well, it can be made. That doesn't mean it's still not very reactive. This can be made. Doesn't mean it's not highly reactive or it is unstable. It breaks down by this electron movement. We can start with any of these arrows. I reckon I would start here. These electrons move down and make pi bond. And let's follow our electrons here. These electrons, which is the single bond left between carbons, move up there and make pi bond, second bond between this C and the O. These electrons move off on the oxygen and become third lone pair. Does everybody agree that that electron movement gives these two separate molecules? Yes. Okay. Where did the third lone pair come from? Well, I showed you right there. This breaks down in that way. Driving force, one thing is entropy. One molecule becomes 2. Another driving forces. Now we don't have 3 oxygens bonded together. So thermodynamically that's more favorable. I'm just telling you that it is. Okay? So there we have cleavage, but guess what? It actually recombines. Because this oxygen then attacks this carbon because it's partial plus. And this is our first attack of a carbonyl. We'll be doing this all second half of the course. Okay? Electrophilic carbon minus likes partial plus. These electrons here, and we kick up the pi bond. Well, like a nucleophilic addition we've done. That would give what? That would give this. I just flipped it around. I've just done this. The oxygen up to become minus, right? Will that become minus? Electrons up. But instead of drawing it up, I drew it down. Which bond did we just make? Right here. Oxygen added to carbonyl, electrons onto oxygen. At this point, this oxygen, which is minus, will do a nucleophilic addition to this. This looks like a carbonyl that's sort of protonated or positive. And these electrons move up onto that, give the 2 lone pair back there, and everything is happy then. And it gives the structure there, and that's called just a molozonide. I'm sorry, not a molozonide, just an ozonide. We get rid of the mal or the mol. So it's no longer a bad ozonide, it's just a regular ozonide. And this is stable. And in this ozonide, you no longer have 3 oxygens bonded together. You only have 2. The other one is not bonded to the other 2. So, alkene reacts with ozone to give first what? A molozonide. But it then undergoes a rearrangement to the good ozonide. In the rearrangement, it breaks apart into two carbonyl compounds. But this is actually something very odd, which we will never see again. It's a carbonyl with another oxygen on the oxygen of the carbonyl. It's called a carbonyl oxide. This is the only place you'll ever see a carbonyl oxide that I've ever seen. But they reconnect, they rebond. And this is the product after reaction of ozone. In the second step, we bring in what?
Magic.
Shown at the top, it's either what? Do I have the 1 and the 2 at the top? Okay. 2 is a totally separate step. It's either what? Zinc metal, or what? Dimethyl sulfide. Both of these are reducing agents. And this is just going to have to be magic. I'm not going to go into mechanism. I don't know that I could. Okay, it's a magic step. Hydrogenation followed by a magic step. Ozonolysis followed by a magic. What does it do? It cleaves the ozonide, and it gives, each carbon becomes a carbonyl. The 2 original alkene carbons become carbonyls. And that's what we said at the beginning. Here's your alkene. What does ozonolysis followed by magic step do? It cleaves the alkene, and the 2 carbons each become what? Carbonyls. There they are. R groups, so 2 R groups on this carbon, thus that product is a ketone. Since there's an H on the other carbon that is not a ketone, it is a aldehyde. Now that could be, both could be H's. Now note, in the products you only have 2 oxygens total. What's the fate of the 3rd oxygen? Well, you either get zinc oxide or you get the sulfoxide of dimethyl sulfoxide. So one of the oxygens is lost to the magic reagent. All right, so this is ozonolysis. Importantly, aldehydes do survive, yeah? Because, first off, let's do the predict product here. What product is the first reaction? So you guys, all this looks familiar for you guys. You had Dr. AJ or somebody else? Yeah, you did all this? Did my presentation the same?
Relatively similar. There was more magic in OChem 1, but yeah.
We didn't cover mechanism in OChem 1.
Did you do mechanism of ozonolysis?
No.
It would just leave the alkene chain and we know that we're going to jump into the
Okay. Well, understanding mechanism I think is important because you're practicing your arrow movement, and hopefully you see how the things were formed, how the bonds were formed, and so that it doesn't have to be purely magic. Second step, I just leave as magic because it's much more convoluted, particularly with zinc, which is probably a radical redox reaction. So, in organic chemistry, when you're doing reactions, predict the product, okay? There's some memorization there, okay? Note card. For example, what does ozonolysis do to an alkene? Quick. It cleaves and each carbon becomes carbonyl. That's just memorization, right? Okay? You got to have a quick starting point. Something for a note card or whatnot. But then the extra information starts coming in. Basically, I don't know that you need any extra information here. If I got products here, you see we're doing ozonolysis, what are we doing? We're cleaving that, right? Each carbon becomes what?
Carbonyl.
Okay. So there's the carbon of the alkene, but you can do this. Instead of this double bonding to another carbon, instead of another carbonene over here, what eventually ends up over here? It ends up being double bonded to an oxygen. So it's just that, double bonding to an oxygen instead of carbon. So there's the oxygen. Well, let's keep the H there. You don't have to, I mean, that's your product on that side. But that's an aldehyde, and remember I like to draw in the H's of aldehydes. Because there is an H here, right? And then what's the other product going to be? Well, it's going to be carbonyl. And then what's on this carbon? Yeah. So in this case, we get what? Two aldehydes.
Okay. So it's not necessarily going to be a ketone and an aldehyde?
No, it depends on what the
okay.
R groups are. In my
Okay.
general example, I showed a ketone. Depends on the R groups.
Okay.
Okay, we can also cleave alkenes in rings. Now this will be one product, not two. Because when you cleave the alkene, it'll still be bonded to the remainder of the ring. Basically, what do we get? You cleave this. In terms of memorization, I mean, this is, you know, the mechanism is more than memorization, but in terms of predicting product, you can just kind of rely on memorization. That is okay in some regards. And so what do we get? This is double bonded to oxygen, and this comes around, and this is double bonded to oxygen, and what's here? Hydrogen. And so I'll show it like that. It's just opened up. Each carbon became carbonyl. It's a single molecule, but we have two carbonyls. One's a ketone, one's an aldehyde. It's magic step, right? So this is the famous ozonolysis of alkenes. Each carbon got oxidized. It's important to be able to go backwards. This is an example showing backwards. What starting material would give those two products by an ozonolysis? And when we say ozonolysis, that includes the magic step. Question?
Yes, not the one before that. Is it possible to open up the entire ring and draw it as a line structure instead of just leave it the way it was and just add the ketone and aldehyde? Does that make sense?
I did open the ring and show it as a line structure.
Yeah, I might can we rotate the bond so that it looks more like that rather than.
I think I know what you're talking about. You can show however you want. Just like if I showed you,
Okay.
asked you to put a hand on the board, you can draw it like that, that.
It would also.
As long as you put the right hand on the board, I mean, you can draw it like that if you want, any way you want. I drew it like that to hopefully maybe help you see coming from the ring. Okay. Yes, all these carbon-carbon bonds are fully rotatable, but I doubt you were ever asked when you were showed to show a product that it had to be shown in a certain way.
No,
As long as you showed the correct product, like this. Show me your right hand. Sorry, I wanted the thumb pointed towards me. I would never say that, right? You good? Okay. Other question? Do that. You can show a product there. We're running out of time. Okay, guess what? You can also do this with KMNO4 and heat. KMNO4, actually any of the big three will do this as well. If you do this cold, it only gives diol. That was on the first page back. Okay. But heat will also cleave. Okay. But guess what? If you cleave this with ozone, you get an aldehyde and a ketone. If you cleave it with KMNO4, you get what? You get a carboxylic acid and a ketone. Why? Because, yes, you first get an aldehyde and a ketone, just like that. But what does KMNO4 do to aldehydes? It oxidizes them to carboxylic acids, right? That's what, okay? So, KMNO4 does the same thing. The problem is aldehydes don't survive when you use KMNO4. All right? Aldehydes are further oxidized. See, back over here where I said aldehyde survives. Now, there is a workup with the ozonolysis where the aldehyde would get oxidized. Did you guys do that? Okay. So some books will do that. Instead of, if you use zinc or dimethyl sulfide, aldehyde will survive. If you use other magic steps, aldehyde maybe will not, which kind of makes sense. But we're not doing that. But if you use these magic steps, aldehyde survives. KMNO4 will do the same thing, but aldehydes don't survive. They get oxidized. Okay, we'll finish this up on Monday, and Monday we may also have a quiz. Okay, we got epoxide reactions. We would include maybe some of this, and we also have NMR. And we said no new lab next week. We'll have some type of review next week and talk about the 8-week lab. Have a good day, guys.